We're going to deal with conditional probability today. The first thing we're going to look at says a brokerage firm wanted to evaluate the performance of its brokers. It separated its brokers into two categories. B was those who used research to make their decisions, and B would be complement with those who did not use research to make their decisions. So we have our B in our top row, our B complement in our second row. It further subdivided that. It then measured whether they picked stocks that went up or down. It again divided those into two groups. A was the group who picked stocks that went up, and A complement those who didn't pick stocks that went up. So those are our columns here. Now we can actually do our regular calculations. We can calculate P of A, which is the probability A over the probability S, or the number of A over the number of S, which would probably be a better example here. And the number of A is simply the number total in this column, which is listed right down here at the bottom. So it's 60 over 100, which is 0.6. Similarly, the probability of A complement is 40 over 100, or 0.4. We can also do the same thing with our other category, B and B complement. Probability of B is 45 over 100, and the probability of B complement is 55 over 100. This is all standard how we've done our calculations before. However, we want to look at it a little bit closer, though. What is the probability that brokers who use research pick the stocks that will go up? Now, in this case, I have 45 total brokers who do research. Right here is this total. And those who do research, 30 of them pick the stock to go up. Now, we're going to calculate our probability the same way. It's the part over the whole, or 30 over 45, which is 0.66 or 2/3. Please note, though, there's a huge difference here. Every probability we've calculated so far has been done on N of S, the number in the sample space. Here we are restricting what we're looking at to a subset of our sample space. We only want to consider those whose stocks went up if and only if they used research. Please understand, this is different than the probability that a broker picks a stock that will go up. Remember, that probability was 60 over 100, which was 0.6. This is what's known as conditional probability. You want to think of it like this. We have two sets. E and F are two events for a particular experiment, and all the events in the sample space S are equally likely. P of E given F, E bar slash F, is the conditional probability that event E occurs given that event F has already occurred. And the way we calculate that is P of E given F is P of E intersect F divided by P of F. So instead of looking at the entire sample space, we restrict our view of events to just F, the probability of F occurring, and we divide it. That's our denominator. Our numerator is their intersection where they both occur. So given that I know F has already occurred, what's the probability that E will occur as well? We can also change this up. Instead of using probabilities, we can use counts using our numbers. So probability E given F is the number of E intersect F divided by the number of F. So I can count the number of ways F occurs, and then that's my denominator, and my numerator is the number of ways E and F occur, their intersection. Please note we can use both of these to calculate our conditional probability, either our probability formula, P of E intersect F over P of F, or a count formula, N of E intersect F over N of F. Again, we're not using the sample space. That is the big difference here. We know event F has already occurred. We only care about this as being the total possible outcome, so this will be our denominator. The event we're looking to measure is not just E, but those that are in E and are also in F, since we're restricting ourselves to F strictly to begin with. This is the formula you need to memorize. This is the one you'll most likely want to put on your note card for the exam. In other words, we already know that event F has occurred. I said that before. So if event F has already happened, what is the probability we now see event E occurring? And this is what P of E given F stands for. Let's look at some examples. Find the probability of A given B complement. Our formula is the probability of N, the number of A intersect B complement, divided by the number of B complement. Well, A is this column here, B complement is our second row, so our numerator is going to be 30. And the number of B complement, the total in B complement, those that didn't use research, was 55. So that's 30 over 55, which is 6 over 11. We can get a couple more practices. The probability of B complement given A. This was different than we just did. We did the probability of A given B complement. If we're given A first, this is the probability of their intersection. Their intersection doesn't change. It's still 30, but the probability of A is actually 60. So this is a different percentage. This is 30 over 60, which is 0.5. Now please check your MyLabs Plus and make sure you're answering it in either fractions or decimals, however it asks for. We can use other things. Probability of A complement given B complement. Again, this is just the number in their intersection divided by the number in B complement. Realize the intersection is always on top, and the second one you have listed is in the denominator. So the number of A complement intersect B complement, that's the second column, second row, so 25. And the number of B complements 55, so 0.4545. Now, are P of A given B and P of B given A the same? Well, let's look at the formulas. P of B given A is their intersection divided by the number of A. Well, A intersect B is 30, and the number of A is 60, so that's 0.5. P of A given B, well, again, the numerator is the same. They're just in different order, but A intersect B and B intersect A is the same. And the number of B in this case is 45. So our denominators are different. So our answer is no, they are not the same. So order does matter here. Let's combine the concepts what we talked about in 7.4 and 7.5. Given probability of E equals 0.56, probability of F is 0.64, probability of union is 0.8, find the probability of E given F. Well, I know the probability of E given F has to have their intersection. I'm not given their intersection to begin with. However, I have my union formula. The union rule says the probability of E union F is the probability of E plus the probability of F minus the probability of their intersection. I know these first three. I don't know the last one. So I'm simply going to plug in. And I'm going to solve for this, and I get the probability of E intersect F is 0.4. Now I can jump in and find the probability of E given F. The probability of E given F is the probability of their intersection divided by the probability of F. I started out calculating the probability of their intersection, which was 0.4, and the probability of F is 0.64, so 5/8, or if you want to write it as a bit of decimal, depending on how it's asked for in MyLabs Plus. All right, we can also use a Venn diagram to calculate conditional probability. The probability of B complement given A. Well, again, this is just the probability of B complement intersect A. Well, B complement is the stuff outside of A, so this 0.3 and this 0.25. A is at least 2.3, so when I look at their intersection, it's just the 0.3. And the probability of A is the entire, all the numbers in the circle added together. So it's 0.3 divided by 0.6, so 0.5. The probability of A complement given B complement. That's the probability of intersections divided by the probability of B complement. Remember, A complement is the outside of A, B complement is outside of B, so their intersection is this 0.25, and the probability of B complement is the stuff outside of B is the 0.3 and the 0.25, so 0.55, so our answer is 0.4545. All right. Given the probability of E is 0.4, the probability of F is 0.5, and the probability of union is 0.7, find the probability of E given F. We're going to kind of combine our concepts. We did a problem just like this a second ago. We didn't have their intersection, but we had their union. So we can find their intersection using our union rule. We know the probability of E union F. We know the probability of E and the probability of F. We don't know this, so we can plug in the three we do know and solve and get their intersection as 0.2. So I fill in my diagram. I get 0.2 here. Probability E was 0.4, so 0.4 minus 0.2 is 0.2. Probability F was 0.5, so 0.5 minus 0.2 is 0.3. And finally, this adds up to 0.7, so this one has to be 0.3 because I know the sum total of all my probabilities has to be 1. So, what's the probability of E given F? Probability of E given F is their intersection divided by the probability of F. Their intersection was 0.2, the probability of F was 0.5, so we get 0.4. Now, just on a side note, we didn't necessarily have to fill in the Venn diagram. We could have gone straight to our formula, but see how everything ties together here. two fair coins are tossed and it's known that at least one is a head, find the probability that both are heads. Well, the probability E given F is the probability of two heads given that at least one head has been flipped. Because that's all we know, is that at least one head is a head. Well, our sample space is flipping two coins. Tails, 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 heads, heads, tails, heads, heads. F is the fact that we've known that it's at least one head. At least one head are these back three. Tails, heads, heads, tails, and heads, heads. E is find the probability that both are heads. Well, the only way that both are heads is if you have heads, heads. So we could do our formula using our probabilities. The probability E given F is the probability of their intersection. Their intersection is just 1 out of 4. Remember, they only intersect at one place, and probability is the number in the event over the number in the sample space. The sample space is 4, so it's 1/4. Probability of F is 3/4, so when you divide, you get 1/3. However, we could also use our second formula, which is just simply the counts. The number in E intersect F. There's only 1 in their intersection. The number in the F is there's 3, and we get 1/3 just like we did in our first one. Let's continue with this. If two fair dice are rolled, find the probability that the sum of the dice is 10, given that the sum is greater than 5. Well, E is the sum is 10, F is the sum is greater than 5. If we just use our counts, the sum is 10 is our diagonal, these 3. Okay? The sum is greater than 5 means the sum could be 6, which is these 5, or 7, which is these 6, or 8, which is these 5, 9, which is these 4, 10, which is these 3, 11, these 2, and 12, this 1. So there's 26 ways for the sum to be greater than 5. So the probability of E intersect F is the probability of their intersection, because they only intersect in 3 places, these 3 where they're all 10, and greater than 5, and then F was 26, so our probability was 3 out of 26. If two fair die are rolled, find the probability that the sum of the dice is 10, given that the first die is 6. E is the sum is 10, F is the dice is 6. The sum is 10. There can only be one way where the sum is 10 and the dice is 6. That's when the other dice is a 4. And the number of ways the red dice is a 6. There's 6 ways having 2 dice where the red dice is 6. So 1/6. 2 cards are drawn from a standard deck, one after another with no replacement. Find the probability the second card is red, given that the first card is red. This is where we're going to start looking ahead, okay? This is a conditional probability where we're going to have to reason through this, okay? A standard deck of cards has 52 cards in it, half of which are black and half of which are red. I want to find the probability that the second card is red, given that the first card is red. This is the probability the second card is red and the first card is red, divided by the probability the first card is red. Again, all I'm talking about is the probability that the second card is red. I don't care about the probability of the first card. I only care about the probability of the second card. If we reason through this, if I've already drawn one red card, that means I'm not replacing the card because it says no replacement. There's only 51 cards left to draw from. If I want a second red card, that means I don't have 26 red cards to choose from because the first one was already red. I only have 25 red cards to choose from. Therefore, my probability is going to be 25 over 51. We're going to have to use this. This is very common to use when we're dealing with cards without replacement, where our odds change because our sample space is changing because we're not replacing that first card. 2 cards are drawn at random without replacement. What is the probability the second card is a heart, given that the first card is the ace of hearts? Well, again, we only care about the second card. The first card was the ace of hearts, which means that originally there was 13 hearts to choose from. Now there's only 12 hearts to choose from. So my numerator is going to be 12. And again, I had 52 cards originally, but I didn't replace it, so now I'm down to 51. So my odds are 12 out of 51. And we actually could reduce that to 4 out of 17, and we should reduce it. 2 cards are drawn at random without replacement. What is the probability the second card is an ace, given that the first card was not an ace? Now, again, we're not replacing things. This one's slightly different because so far what we've been doing is we've been taking one away from our numerator and one away from our denominator on all our probabilities. But here, notice the first card is not an ace. So my first card is something completely different. So when I go to draw a second card, there are still 4 aces to choose from. However, there's not 52 cards to choose from. There's only 51 cards to choose from. So my probability is 4 out of 51. Let's expand our rule. We knew the probability of E given F was the probability of their intersection divided by the probability of F. If we move the probability of F over, we wind up with a new formula for the intersection. The probability of E intersect F equals the probability of F times the probability of E given F. Now, we also know the probability of intersect F is the probability of E times the probability of F given E, because we could manipulate both of these formulas. So we have 2 ways of calculating these intersections. We just need to know how we pair them up. Notice the individual one, the F here, is the second one in the order here. The E here is the second one in the order here. It is the conditional one. In a class of students, 40% are men and 60% are women. 30% of the women are marketing majors. Find the probability that a student chosen at random is a female major in marketing. We'll take E to be the event that the person is majoring in marketing, and F is the event that the person is a woman. The probability of E intersect F is the probability of F times the probability of E given F. We know both of these. We know the probability that the person is a woman is 60%. We also know that 30% of the women are marketing majors. Therefore, if I choose a woman, there's a 30% chance that she will be a marketing major. So 0.6 times 0.3 is 0.18. So if I simply choose one person at random, there's an 18% chance I will choose a female marketing major. Let's look at another example. 2 cards are drawn without replacement from an ordinary deck. Find the probability that 2 hearts are drawn. Now notice I'm not just talking about a second card here. I want the probability that I draw the first card as a heart and the second card as a heart. So the probability of drawing a heart is 13 out of 52, which is 1/4. Now the probability of drawing a second heart after drawing a first heart, this is your conditional probability. Again, there's only 1 heart drawn, so there's only 12 hearts left and 51 cards to choose from, so that's 4 out of 17. Now to do both of these events means I have to multiply these two, okay? That's my intersection formula. The probability of doing E and F together, in other words, drawing a heart and drawing a second heart, given the fact drawing a heart first and a heart second, is P of E times P of F given E. So this is 1/4 times 4/17, which is 1/17. Sometimes it's actually easier to create a tree diagram than to actually calculate all the possible intersections of the event. Just to let you know, the fewer possible outcomes for each event, the easier the tree diagram is to create. Let's look at some examples. You have 2 employees, A and B. Employee A completes 3 times as many jobs as employee B, and employee A completes jobs satisfactorily 2/3 of the time, while employee B only does satisfactory work 3/5 of the time. So let's see how we'd set this up. Event E is event an employee is chosen, and event F is an event of how well the job was done. I'm going to make one column for each event. I have employee A and B. I have 2 branches, because I'll either choose A or choose B. Satisfactory or unsatisfactory for each person, which leaves me a total of 4 different branches. Now the odds of me choosing, the probability of me choosing A is actually 3/4, because it says employee A completes 3 times as many jobs as employee B. So 3 jobs for employee A for every 1 job for employee B. So out of 4 jobs completed, 3 of those will belong to employee A, which means if he completes 3/4 of the jobs, employee B completes 1/4 of the job. Now employee A's satisfactory rate is 2/3 of the time. So 2/3 of his jobs will be satisfactory compared to 1/3 unsatisfactory. Whereas employee B, 3/5 will be satisfactory, versus 2/5 unsatisfactory. Remember, these pairs always have to add up to 1. Now let's figure out our probabilities. The probabilities here is the probability of E intersect F equals the probability E times the probability F given E. Well, what we've done is we've created all these probabilities in our branches. So to calculate our first probability, we just follow down the branch. Probability of A and satisfactory would be 3/4 times 2/3, which is 1/2, just following the numbers straight down the branch. The probability of A intersect U, in other words, the probability of choosing employee A and having be unsatisfactory, is 3/4 times 1/3, which is 1/4. The probability of B intersect S, which is the probability of choosing employee B and having being satisfactory, is 1/4 times 3/5, which is 3/20. And finally, the probability of B intersect U is 1/4 times 2/5, which is 1/10. Now please note, if we actually got a common denominator, added up all these fractions, it would be 1, because this represents all our possible outcomes, choosing either employee A or B and having the job be satisfactory or not satisfactory. So if we look at this and start asking ourselves questions, what is the probability that A is chosen and does a satisfactory job? Well, we just calculated that right here. It's 1/2. We no longer have to go in and plug in any formulas. We have our tree. Our tree is going to give us all our answers. What is the probability that B is chosen and does a satisfactory job? Well, here's B, here's satisfactory, there's the probability, 3 out of 20. What is the probability that it is a satisfactory job? Well, this is where we have to use a little bit of reasoning, because it always says the job is satisfactory, which it means it could be A unsatisfactory, or it could be B unsatisfactory, which means we simply have to add these two together, which entails getting a common denominator. So 1/2 plus 3 over 20 is 10 over 20 plus 3 over 20. So 13 out of 20 is our probability. Let's look at another example. You root for 2 sports teams. Team A you'll root for 4 times as often as you'll root for Team B. Team A wins 9/10 of the time and Team B wins 7/10 of the time. Create a team tree diagram for the intersection of the teams and their winnings. So event E is choosing a team. Event F is the event of whether the team wins or not. So here's the team and the win, and we have event A and B. And again, we only have 2 possible outcomes, wins and losses. Now, if we had 3 outcomes, each of these would have 3 branches coming off of here. And the total number of branches will be the number of branches you have for each event. So in this case, 2 times 2 for each event is 4. So we need the probability of rooting for Team A. Well, it says you root for Team A 4 times as often as you root for Team B. So for every 1 time you root for Team B, you root 4 times for Team A. So 4/5 of the time you'll root for Team A, whereas only 1/5 of the time you'll root for Team B. Now Team A wins 9/10 of the time, which means they lose 1/10 of the time. Similarly, Team B wins 7/10 of the time, which means they'll lose 3/10 of the time. We're going to do the same thing here. We're just going to use our branches to calculate our conditional probabilities. And we're going to multiply. So we get 18 over 25, 2 over 25, 7 over 50, and 3 over 50. And again, the total is just 1. Let's look at another example. Bob has a bag of M&Ms with 8 green, 4 yellow, 6 blue, 9 orange, 2 red, and 12 brown. Calculate P, the probability Bob draws a brown M&M second after drawing a green M&M first. So can this be done without making a tree? Yeah, we can. We can do it like we've done before. We'll let G be the event that you draw the green first and B be the event you draw the brown second. So it's P of G times P of B given G. Now G is actually a little bit easier to calculate because G is just 8 out of 42. I have 8 green and 42 total M&Ms. Now, I've already drawn an M&M. We're going to assume you're not going to put it back. We're assuming you're going to go ahead and eat it. So that means I still have 12 brown to choose from, but only 41 M&Ms to pick from overall. Now we're just going to simplify and multiply out for our answer. Let's look at another example of a tree, because sometimes it can be very helpful. The Environmental Protection Agency is looking to inspect plants, 3 in Chicago, 2 in LA, and 1 in New York. Due to lack of resources, they can only inspect 2 of the plants. Create a table showing the conditional probabilities of each pair of plants being selected for inspection. Here is our table. We will talk about this in a second. Let's first figure out how we got this numbers. 1/2, 1/3, 1/6. If you remember, there's 3 in Chicago, so 3 out of 6 is 1/2. There's 2 in LA. 2 out of 6 is 1/3. There's 1 in New York. 1 out of 6 is 1/6. All I did was take the number in each city and divide it by the total, and those gave me the probability of each one of these being chosen first. Next question. How do we get these probabilities here? Well, again, we started out with 3 in Chicago, 2 in LA, and 1 in New York. However, if I go to Chicago first, that means there's only 2 Chicago left and only 5 total to choose from, so 2/5. There's still 2 LA left, so 2/5, and 1 New York left, so 1/5. I did the same thing down here. The only thing I'm doing is backing out LA now. There's 3 Chicago to begin with. There's still 3 left and 5 cities left to choose from, so 3/5, because I've already chosen LA. There's now only 1 LA because I'm already in LA, and again 5 total, so 1/5, and there's still 1 New York, so 1/5 down here. This last one, notice there's only 2 branches. Well, the reason there's only 2 branches is that there's only 1 New York, and you already went to New York, so you can't choose it again. So that means that there's 3/5 chance of choosing Chicago after going to New York, and 2/5 chance of choosing LA after going to New York. Again, we have our branches. We can calculate our probabilities, just multiplying down the branch. 1/2 times 2/5 is 1/5. 1/2 times 1/5 is 1/10. And we can choose all these probabilities. Notice our probabilities are written in the order of the city. Chicago, 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 LA, Chicago, New York, LA, Chicago, LA, LA, and etc. So now we can answer our questions. What is the probability of visiting Chicago and then New York? Well, Chicago and then New York is right here, this probability 1/10. What is the probability of visiting both plants in LA? Well, LA and LA is right here, 1/15. What is the probability of visiting Chicago first? Well, Chicago first is just right here. It's just this branch. We don't care anything about the second outcomes. It is only asking about our first outcome, so 1/2. Or if we want to look at these, we can choose all 3 of these options, and if we add these together, you will wind up with 1/2 as well, because all of these add up to 1. What is the probability of visiting the New York plant? This is where we have to think about it, because it doesn't say New York first or second. So we need to look over here. There's New York, there's New York, here's New York, and here's New York. All we need to do now is take these probabilities, add them together. It will take getting a common denominator, and we wind up with 10/30, or 1/3. Let's look at some more examples. 2 cards are drawn at random from a standard deck of cards, one after the other without replacement. Draw a tree diagram showing the probability the first card is a heart and the second card is red. Well, the first card, a heart, is 13 out of 52, or 1/4. The second card is red is obviously what's remaining, which is 39 out of 52, or 3/4. Our second choice, a red card or a black card. Well, I already knew I drew 1 red card from the heart, so I don't have, again, we're dealing with red, not just hearts, so there was 26 red cards originally. Now I only have 25 left and 51 to choose from. Second one is a black card. Well, if I drew a heart to begin with, there's still 26 black cards in there and 51 left. Notice again that these add up to 1. Now, let's just say we did not choose a heart. What's the probability of getting a red card or a black card? I'm sorry, let's answer this question. What's the probability the first card is a heart and the second card is black? So 1/4 times 26 over 51, and reduce that to 0.1275, so we get the same concept with our tree. What is the probability that the second card is black? Well, this is where it gets a bit tricky at, because we know the first card is is not a heart. We do not know these probabilities, since we do not know if that first card was a diamond or a club or a spade. All we know is it's not a heart, which causes problems for us because we can't figure out this probability initially. However, we need to take a different approach, because it says, what is the probability that the second card is black? Well, if we simply divide the top branch into diamonds, spades, and clubs, we could do it that way. Excuse me, the bottom branch, the second branch. Or, since we all care about the second card, we could simplify and divide the first category into red and black instead of heart and non-heart. Here's the probability of red, here's the probability of black. Now, once we know it's a red card, there's 25-51% chance of getting a red card because there's one less red card versus 26 out of 51 for black. And the opposite down here for the first card was black. Now, if we ask the probability the second card is black, we have two options. I either chose red black or I chose black black. So we have to take both of these, multiply, and get our answers for each branch, and find out the probability the second card is black is actually just 1/2. We're going to wrap up with our conversation on independence. Events E and F are independent if the knowledge of E has occurred gives no probability or information about the occurrence or non-occurrence of E. That is, P of F is the same as P of F given E. In other words, the fact that E occurs for P of F given E has no impact on the probability of F occurring. This would probably be a better example of, say, dice. Actually, let's look at our formulas first. Events E and F are independent events if probability of F given E equals probability of F, or the probability of E given F equals the probability of E. Two dice are rolled. Are the following events independent? The first is an even number, the second is an odd number. These are independent since the second event does not depend on the first event. The outcome of my second dice has nothing to do with the outcome of my first dice. However, if I'm drawing cards without replacement, in this case, are the following events independent? The first card is a heart, the second card is a heart. Well, we already know that the first card being a heart affects the probability of the second card being a heart. Same as if the first heart was a diamond, it would affect the probability of the second card being a heart. This is a dependent event since the second event depends on the first event. Events E and F are independent if and only if the probability of E intersect F equals the probability of E times the probability of F, which is really nice because this is a very simple calculation. Let's look at some examples of this. A and B are independent events with the probability of A 1/7 and the probability of B 1/3. Find the probability of A intersect B and the probability of A union B. Well, their intersection is just the product of the two, 1/3 times 1/7 times 1/3, which is 1/21. We can go back to our union rule. Probability of A union B is the probability of A plus the probability of B minus their probability of their intersection. We already have these numbers. Now it's just a matter of getting an LCD and getting an answer of 9/21 and reducing it to 3/7. If the probability of Alabama losing on any given weekend is 0.5 and the probability of Auburn losing on any given weekend is 0.7, what is the probability of Auburn losing and Alabama losing? These are independent events since the first one doesn't depend on the second. So the probability of their intersection, that's an AND statement, is the probability of E times the probability of F. So the probability of both teams lose is 0.0035. What's the probability of Alabama or Auburn losing? This is an OR statement, so we're going to use our OR formula. We already know the probability of Alabama losing was 0.05, Auburn losing was 0.07, their intersection was 0.0035, so the probability of both teams losing on any given day, or either team losing, either or, is 0.1165. And we'll close out one last example with M&Ms. Alan and Bob are given two identical packs of M&Ms. They each have a bag of M&Ms with the following. Calculate the probability Alan draws a green M&M. That's simply 8 out of 42, or 4/21. Probability that Bob draws a brown M&M. This is simply 12 out of 42, which is 2/7. Again, each have separate bags, so when Bob draws, whatever Alan draws has no effect on what Bob draws. And again, we can calculate their intersection and their union. Their intersection is just the product of the two. Their union, you use our union rule.